work. But if you're cooperating with the other reference frame, then and interacting with each other, then you can determine which one is the one moving. But it still doesn't violate the special relativity because it's taking certain cooperation by you contacting that person, and then they're contacting you with an electromagnetic wave, you see, and you're talking to each other. So that's kind of interesting that one has a different effect than the other. I don't know if over here, back on the other page, they show you the Doppler effect for light waves. The Doppler effect has a lot of uses. I always like the radar use. For example, the police. Astronomy uses are interesting also because you can find the Doppler effect is the one that proved the universe is expanding by studying the spectral lines of stars and looking at the wavelength that they emit, which has shifted. So if a star's wavelength is redshifted towards the red end of the spectrum, then that star is moving away from you, right? And in Mount Wilson Observatory, that's where Edwin Hubble proved that most stars and galaxies are receding away from us because they show a red shift versus a blue shift. So their wavelength is expanding, right? So that means that they are moving away from us. So that from there, he proved that the universe is expanding, and then from there we showed that the Big Bang Theory is a most viable explanation of the beginning of the universe. Let's see what other uses. Radar is another use. Doppler effect is used in some types of radar to measure the velocity of detected objects. A radar beam is fired at a moving target. Motor cars, police use radar to detect speeding motorists. Each successive radar wave has to travel farther to reach the car before being reflected and redetected near the source. As each wave has to move farther, the gap between each wave increases, increasing the wavelength. In some situations, the radar beam is fired at the moving car as it approaches, in which case each successive wave travels a lesser distance. In either situation, calculations from the Doppler effect accurately determines the car's velocity. Moreover, the proximity fuse developed during World War II relies upon Doppler radar to detonate explosives at the correct time. Because the Doppler shift affects the wave incident upon the target as well as the wave reflected back to the radar, right? So this is a double Doppler effect. The wave is going, and if the observer is moving, reflects off that. So the perceived frequency of the observer is changed, but then reflects off the observer, and now the observer acts as the source, right? So it says here, because the Doppler shift affects the wave and reflected back to the radar, the change in frequency observed by a radar due to a target moving at relative velocity delta v is twice that from the same target emitting the wave. See, in this case, the car is not the one emitting the wave. It's just acting as the observer, then acting as the source of the reflected wave. So then it's a double Doppler effect. Medical uses of Doppler effect. An echocardiogram can, within certain limits, produce an accurate assessment of the direction of blood flow and the velocity of blood and cardiac tissue at any arbitrary point using the Doppler effect. One of the limitations is that the ultrasound beam should be as parallel to the blood flow as possible. Velocity measurements allow assessment of cardiac valve areas and function, abnormal communication between the left and right side of the heart, leaking of blood through the valves, and calculations of the cardiac output. Awesome, isn't that? So any kind of medical use of science is just wonderful. Although Doppler has been synonymous with velocity measurement in medical imaging, in many cases it is not the frequency shift of the received signal that is measured, but the phase shift. Velocity measurements of blood flow are also used in other fields of medical ultrasonography, such as obstetric ultrasonography and neurology. Wow, awesome. Flow measurements, velocity profile, satellite communication. See? So imagine you have a satellite that's moving around the Earth, velocity of the satellite. But the Doppler shift can only calculate the radial velocity of the satellite, or the coming towards you portion. Right? If something is moving perpendicular to you, it has no Doppler shift. But if it's moving at a random direction, then you can determine the radial component of it, right? The towards you or the away from you. So here is a car moving this way. Well, this is spherical coordinates, right? Theta and phi. So geometry for Doppler effects, variables V mob, which is V mobile, is the velocity of the mobile station. V satellite is the velocity of the satellite. V relative satellite is the relative speed of the satellite. Phi is the elevation angle. And theta is the driving direction with respect to the satellite. Wow. Wow, even in music, audio, it says the Leslie speaker, most commonly associated with and predominantly used with the famous Hammond organ, takes advantage of the Doppler effect by using the electric motor to rotate the acoustic horn around the loudspeaker, sending its sound in a circle. This results at the listener's ear in rapidly fluctuating frequencies of the keyboard. Laser Doppler micrometer, so all the developments of the Doppler effect. Developmental biology, segmentation of vertebrate embryos and gene expression. Sweep across the presumulative mesoderm. So now this is stuff beyond my knowledge. It's biology. What's inverse Doppler effect? Since 1968, scientists such as Victor Veslango have speculated about the possibility of an inverse Doppler effect. The size of the Doppler shift depends on the refractive index of the medium, the wave is traveling. But some materials are capable of negative refraction, which should lead to a Doppler shift that works in a direction opposite that of a conventional Doppler shift. The experiment that claimed to have detected this effect was conducted by Nigel Sidon and Trevor Kirk of Bristol, United Kingdom in 2003. So you can read about that. So remember, you have a research paper you can do at the end of the semester. It could be a good topic to do it on, and it's for extra credit. So as you see, there's a lot of good uses. Take anything that we've learned about and then talk about it, and also relate it to some real live instruments that use that stuff in the real world. Okay, so let's say there is a car driving like this, and then this is imagine this is the road. There's a nasty police officer here. So the police officer is pointing the radar gun, right? What's the frequency of radar usually? General, roughly. So it's about 10.5 gigahertz. Okay, so now if the frequency is shot like this, right, and then it's going to come back. So first, the car acts as the observer, right? So the velocity of the car in the radial direction. So let's say this angle is, let's say 35 degrees. So this angle is 35. So at the instant that you are 35 degrees from the police, he shoots the radar beam and then it comes back and reflects off, right? So let's say the F is 10.5. What's going to be the perceived frequency of this guy? F prime is going to be what? F, velocity of the sound wave, 343. Let's see here. In this case, the source is not moving, right? Yeah. Only the observer is moving. So he's the observer. So that means I use the top, right? The observer, and it's plus. So and then it's going to be this guy. V, let's see here. Cosine of 35.
Over cosine.
Right? So this V, the one that's coming this way, because it's a triangle like this, is a portion of the total velocity of the velocity of the police car, right? So V, we can call it V parallel. Why? Because it's along the direction of the police car's line of sight, you see? And then this is V, so then this is 35. So we can say V parallel is V cos 35. Over, and then this guy's velocity is 0, so it's just 343, right? And then you're going to have, so now when the wave is reflected, he acts as the source, right? So now he acts as the observer. So F double prime is equal to F prime, because since he receives the waves with that frequency, then he emits the waves with that frequency, right? He observes it at that frequency F prime, then he emits it at that frequency F prime, but then this guy observes it with a frequency of F double prime, right? So then F prime times 343, so now he perceives the source as coming towards him, right? So then it's going to be 343 minus V cos 35. Okay, so then let's say when he comes back to him, the radar gun receives 10.8 gigahertz. So from there, how fast is that guy driving? And should we give him a ticket? Okay, so let's say the speed limit is 50 miles an hour. So this would be 10.8, and then F prime would equal this, right? So then that one you substitute here, and then F would be what? 10.5, right? So 10.5, 343 plus V cos 35 over 343. 343 over 343 minus V cos 35. So this is what I meant by a double Doppler effect. Going, bouncing, coming back. You see? And then that one cancels. Then you have here 10.8 is equal to 10.5. If you want, you can do some more stuff and simplify it and solve it yourself. This one, I think I would probably just do it that way. 10.8, cross multiply this, multiply it by 343, minus 10.8 v cos 35. So I cross multiplied it, distributed this into that, then I distribute this into there, 10.5, 343, plus 10.5 v cos 35. Right? And then it's just one more step for you to simplify, and you already have the equation. I would take this and take this and reading it over here, 10.8, 343 minus 10.5, 343, divided by, take this that has a v, bring it on this side, factor out the v, right? And then just have everything else, which is 10.8 cos 35 plus, right, this one goes over there, plus 10.5 cos 35. Right? And then you can even factor out more and make it even more simpler. 10.8 minus 10.5 is 0.3, right? So that's 0.3, 343 over 10.8 plus 10.5 is 13, 1, 21, right? 21.3
yes.
cos 35. See, for this, it was better that you do it yourself versus putting this in solver. Just a couple steps that it requires. Now you know the velocity of the car. Well, the instrument that the police officer is using does this all for you, right? It receives the wave and then it says, he's driving at this speed. Now you fulfilled your quota of the day. You can give him a ticket and go home, right? Because you're just missing one ticket before you go home. Then the happy face comes up. That's it, you get to go home or to the donut shop, right? Sorry if any police officers are watching. I respect you guys.
I like have a question. Since you do it like in 2 steps, if you put it in 1 step, is it possible to do that? Since like,
yeah, you know, I mean, once you've done this, you know how it's gonna work. You can almost do it in 1 step, but I'd rather show you what's happening here,
yeah.
step by step, you know.
Since I wave, it's like it goes up there and then it comes back.
Exactly.
That's why it kind of like travels like twice. Go there and come back.
Yeah. So what is the velocity? What answer do you get?
Should it be 0.5 or 0.3?
10.8 minus 10.5. Oh yeah, 0.3.
I got 5.89.
5.89 meters per second. Okay, he should get a ticket because he's going too slow. Right? That's nothing. Okay, you can still go home. Sad face for the guy. He can't win. He goes too slow. He goes too slow, it's a ticket. He goes too fast, it's a ticket. So that means I should have made this a little more, right? 10 point, maybe like 11.1 or something to make it that he was speeding up. Okay, how about if he's driving this way at 20 meters per second? Now let's make this more. Let's make it 12.2. So now the police is driving this way as he's watching you. He's going 20 meters per second. And you're going at V. Find out what V is now. But the shift is larger, from 10.5 to 12.2. So make some correction. okay? The velocity of the police is 20. Maybe you could still do it in one step, right? You're trying to figure that out all in one.
Yeah, trying to do it. Because like they're both moving.